think we'll wait another minute or two and then we'll kick this thing off. Okay, we'll fire off now. So first off, I want to thank everybody for joining us today on this webinar. We're going to be talking about drilled-in displacement piles, and our presenter is going to be Nathan Matthews with Ideal Group, and he's very knowledgeable about drilled-in displacement piles and should be able to answer any questions you guys may have. We ask that you hold the questions till the end, and we'll go ahead and let Nathan kick this thing off.
All right, thanks, Sam. Just briefly what we're going to go over today, a little intro, and I try to wrap this all up in a 45-minute presentation where we talk a little bit about the installation, the equipment, and then we kind of get into some design stuff just to show you the basics of how we design these piles, some geotechnical design and load cases and things like and case studies we have. So like Sam said, I'm the senior design engineer with the Ideal Group. We're a manufacturer of helical piles and a drilled-in displacement pile system called Stelcor. And how we're related here, Intech is our distribution partner throughout a big part of the country. So the basics of the drilled-in displacement pile. This particular one here, at its core there is a steel core. So this drilled-in displacement pile is continuously screwed into the ground and gravity grouted from the top of the hole. At the core of it there is the steel pipe, that steel core. All this stuff stays in the ground. Okay, so we start with our steel pipe. That might be 5.5-inch Schedule 80, 7-inch, 453 wall. We can even go larger. But the beginning of it at the heart there is the steel pipe core. So if we zoom in on the first section, the lead section is what we'll call it. There's three important parts of this part of the pile. We refer to them as drive, displace, deform. For those of you familiar with helical piles, that drive plate there looks pretty similar, right? It has a similar function too, is that it helps pull the pile in the ground. From a design standpoint, 95% of our projects, Stelcor is a friction pile because we end up with a grout column. We'll see some pretty cool pictures of some exhumed Stelcors here soon. But 95% of the time, we don't use end bearing with Stelcor. It's generally a friction pile. So our drive plate with the blue box over there is the first thing. The blue box moved up around it. I want you to focus on not the little tooth sticking out, we'll look at that next, but the displacement head. As we're spinning Stelcor in the ground, this displacement head is creating an annulus by pushing the soil outward, and we have a good head flow of grout. So as we're displacing it, we're replacing that displaced soil with grout. So that displacement head is placed about 5 feet up the whole shaft of the pile, every 5 foot or so. We, by and large, understand that this first displacement head does the majority of the work of opening the hole and keeping it open. But just to get the grout take that we've wanted through some R&D and stuff like that, we have a theoretical grout take. We found that having those extra displacement heads can help in some type of soil conditions. So the next two parts of this system are pretty cool. The deformation structure. That tooth, that's the little blue boxes around, sticks out 3 inches past the displacement head. So you can see some exhumed piles there. For the geotechnical engineers in the group, that's a pretty cool looking grout column because that gets really good bond values. So we see our load testing shows we do see some pretty good design capacities over a traditional regular gravity grouted pile from a geotechnical standpoint. So that's the deformation structure. One thing that's unique is we have a reverse grout auger that extends the entire length of the pile. The diameter of this is smaller than the displacement head by about 3 inches. What this does is it continuously just moves and pulls the grout as we pull down, as we open the hole with the displacement head. One thing that I think is cool about it is if you look at the welds along this thing, you can develop the full strength of the pile shaft with this displacement head if it needs to do that. Essentially, I also think it provides some good confinement of the grout between the flights there. And it provides very good load transfer. If you think about, I try to compare this to rebar. Rebar has deformations on it, so you can develop the full strength of the rebar in concrete. This reverse grout auger has the function of pulling grout down, but it also does provide effective load transfer from the steel pipe to the grout to the soil. Now, most of the time, you're going to see the limiting factor is grout to soil. But I have seen some dynamic load tests on smooth shaft piles that had grout where they, in tougher soil conditions, where the third-party testing agency, what they thought was happening was the grout was coming debonded from the smooth shaft. With this reverse grout auger, we don't have that problem with this drilled-in displacement pile. And I kind of beat this drum here a little bit again because I like that depiction on the right there of the load transfer of your grout column. And I also, for those of us that have designed foundations, concrete foundations, drilled shafts, you spend a lot of time in ACI 318, the concrete code, making sure your anchor bolts don't pull out of the concrete. And while we don't use J bolts and L bolts down there much anymore, headed bolts, there's usually some kind of anchorage for your anchor bolts. And here again, I think that reverse grout auger does provide that effective load transfer and anchorage. One of the last parts is, if you look at that picture, you'll notice where we're grouting that pile. We create an annulus, essentially pull it out, create a little grout hole around this thing, and we grout outside of it. We have these 1.8" diameter holes, grout port space throughout the pile shaft. And what that does, it allows us to grout in the exterior, and we have our neat flowable cement mix here, grout mix, that flows to the hole under just enough pressure to get there, and it allows the mix, the grout, to get inside the pipe as well as be outside of it. One of the first jobs I went to with this particular product, they got done, they finished it, and I couldn't help myself. I had to look down the middle of the pipe to make sure that the grout was at the same level as it was at on the outside, and it was. So we get the good grout take there. The other thing I should mention on this particular pile, at the bottom of it, just beneath the drive plate, we actually do close that off. There's a little plate welded up inside of it. Generally, we'll create a soil plug, but we just block that off so then it's got grout all the way up and down it. And there's just a nice picture of an exhumed one in some very sandy soil in Florida. So that's the basics of this system. So I think it's important anytime we're talking about deep foundations, and if we understand helical piles, or you can take drilled shafts to rock, you can do all this stuff. There's a busy slide here, but on the right-hand side, the design capacity is where I want to focus, specifically on these bottom two rows here. This is kind of the world we're living in as far as common loading. We've gone up to 500 kips with some larger ones and things like that, but these are allowable loads per IBC, I believe. So we're living in this 250, 300, 340 kip type range in compression and tension as well. So that's just kind of, we group piles, we do stuff like that, but I just think it's important to understand what we're working with here. And then just the part number. I mean, it's, it just, if we look over here, it's on the second row from on the bottom here where my cursor is. 1600, that's my grout diameter, nominal grout diameter. 5.5, 3/6 is just the pipe shaft and thickness. And then the 18, 16, 13. 18 is my drive plate diameter. 16 is my deformation structure. 13 is my displacement displacement head. 8 is the diameter of my grout auger. And then 3 is we have 3 bolts per connection. That's just our way of keeping our mind wrapped around that. So the other thing I'd like to point out in this table here is under installation here, we have max torque. So we do measure torque when we're putting in this displacement pile system, not as a means of capacity like you might with a helical pile, but mostly because we have pipe shafts out there that do have a torque rating on them. So we prefer, we don't want contractors breaking pipe if they're not measuring torque and aren't careful with what they're doing. So with those torque limits, we also understand that we're not going to put this in rock. If we get in some very dense soils, it may not be a great application for this particular system. When you get into stuff like that, that might be where you start looking at a hollow bar micropile or something like that. And then we generally have our contractors match or exceed the torque rating of the shaft just so we can maximize it if we need to. So some advantages of a drill displacement pile. There's a crossover between these and other smaller types of piles too. Some of the loadings and some other advantages we'll look at later are cases where you might look at looking at a design for something like this. Limited overhead access. I did a job here recently in the Midwest where there's 12 feet of overhead access with, I believe it was 150 kips in compression, 35 in tension, and 5 or 6 kips in shear. We did 5-foot sticks with sections with this. Side access, it was also not only, they hired an auger cast contractor to do the work, but they couldn't get their rig out to actually get on the site, much less with the 12-foot overhead access. We see a lot of success. We don't create spoils with this system. And we do see that when you start getting higher loads and you have to start hauling off spoils, that can get very expensive if they're contaminated especially. I'll look at a load case later about some vibrations for nearby structures and things like that. And the load capacities, we looked at that. So we'll look at some of the geotechnical capacities we can get to. And this is a mechanical displacement pile. So in similar soil conditions, it should be predictable and repeatable from one pile to the next. So some of the installation that you may see on site, this is a pretty limited access setup that we have there, but you're going to have your drive head because you're spinning these in the ground. Again, we recommend that drive head match or exceed the torque of the shaft, and those are 2 common shafts that we use, 5.5, 7-inch, and their corresponding torque ratings. We do have a rental fleet for when our installation partners get in situations like in the picture here where we have limited access set up and stuff like that. And you also have a torque motor. Like I said, the torque motor is just there to make sure that we're not exceeding our allowable torque on our pipe shaft. You also have with that, so we're mixing grout. We like we prefer a high shear colloidal mixer. I believe Intech has probably this setup right here, I think. And all that high shear colloidal mixer is doing is making sure you're getting a good clean, mix, and there's not clumps in it and stuff like that. So it's that good flowable fill that'll get to the hole and get through our grout ports and stuff like that. I've had contractors with the flow meter on site. I know that there's experienced laborers out there who operate grout plants who are very skilled at breaking a bag and doing 5 gallons of water, which is about a 4:4 cement water ratio. This flow meter here, and they can keep track of that, but this flow meter here is just another QA/QC thing that you can have on site can be very valuable. And then the mud balance there, that's just comparing your weight of your specific gravity of your grout to water, and that's a correlation to your grout strength as well too. Pretty cheap and easy way to have a little extra QA/QC in the field. So I get this question a lot. Well, how much does it cost? Well, as we probably all know, that can depend on a lot of things. But I want to give this to a contractor. I want to give this to just have an idea for people what it's going to cost, like what it may cost. And you can spin these things in, if they're 7, 10-foot extensions. With this one here, I'm going to show you in this video, is much higher than that. Most of our partners will say, I don't know, I'll start with 400 or 500 feet a day, just if I have good access and I can, I'm not going from one side of the site to the other to get my extensions and stuff like that. If I just look at a very common pile shaft, a 5.5, 361, that's 30 foot long, we'll just say, your material costs might be $1,500. We try to not compare it to an auger cast pile or something like that because that's a different animal. I tell people, if you can, I've even said this over the years about any type of foundation system, if you can do a spread footing or continuous footing, or you're in some stiff clay and a drilled shaft, guy can go out there and keep the hole open, you're probably going to do that because you're going to get a lot of bids. In situations that we talked about earlier, and even some situations where this was just the best option, that's where you need to start looking at this. We do designs in-house. We've worked with Sam and his team there too. So they're knowledgeable on the process as well. We do like to have pre-bid meetings, and then on the first, if it's a contractor's first project, somebody from Ideal or Intech will be out there to provide that field support. And I'm going to show you a quick video here, just kind of see so you can see how it's very simple how it goes in. They put the lead in, so that's an extension. Like I said, that grout is just being pumped under enough pressure to get to the hole. There's a displacement head right above that big coupler, right about where that guy's knees are. And that's the reverse grout auger going continuously up the pile shaft. You'll zoom up, you'll pan up here in a little bit, you'll see another displacement head as he goes up. There's the other displacement head coming around. And then you're going to go to the top, you're going to see your tooling. You'll see your torque indicator, you'll see your drive head. You can see that it's not a limited access situation there. I think they were next to an existing building. They were next to an existing building with some of the piles. Another situation where we've had where these might be ineffective, if you have 20 piles that's limited access or next to an existing building, you have another 20 that are wide open. Instead of doing 2 rigs, 2 machines, they might bring 1 machine out and do all just drill displacement piles because they're doing half the job there anyway. So that's the basics of the installation. Pretty simple installation with equipment that's readily available. So I'm going to go into the design a little bit, and I go into this, I think probably most experienced engineers could probably wrap their head around this pretty well or pretty quickly if they don't already know. But I do this because I tell engineers we design per a building code, usually the IBC. We've done a lot of work in New York City. They have their own building code. Chicago has their own requirements. LA has their own requirements. But I just put this out there just so people see it's not something it's just an open book. So this is what we use out of the IBC for stresses on the material, the grout and the steel. So we use out of table 1810 there, a third of our F prime C because it's cast in place. The area of our grout for axial, we only rely on the grout inside the pipe. It generally doesn't control from a structural standpoint, but it's less discussion with building code officials and things like that if we just start with that process. So the area of our grout's the idea of our steel core. Allowable stress on steel and compression, pipes or tubes for micropiles. So most steel core piles are 80 KSI, so that 0.4 FY is 32 KSI, that generally controls. And then on allowable stress on steel and tension, other pipes or tubes, so that 32 KSI on 0.5 times FY generally controls there too. So all right out of the building code. A simple example here, we got a unfactored service design load with 200 kips, not factored. We generally live in an ASD world. We can do LRFD designs, but this is generally where we start. I have a tension load of 100 kips, and let's say I'm going to go with this 12-inch diameter grout column with a 550361, 12-inch grout column. So my steel core is at 5.5 361 pipe. My area, my grout's the ID of that. So that's just a calculation, right? So you got 4,000 PSI times 18 square inches with your 3.3 resistance factor, safety factor. So you get 24 kips roughly out of the grout. Go through the same process with the compression in the steel. So compression there in steel, 186 kips. So 210 kips allowable. Tension, comes out to be 186 kips there too. So with the 3.2, so that's the basics of a simple axial design, which, you know, I would say roughly half or more than our designs require some lateral resistance too. And for those of you in the design world, you're probably familiar with L-Pile by Insoft, very well-known software out there. And L-Pile, for those of you that don't know, you can put loads on it and it'll predict deflection depending on the fixity or how far up in the pile cap you are, and it'll tell you what kind of stresses your pile is seeing when it's moving. So they have a very cool option in there that looks a lot like our system to me, which is that round shaft with a casing and core insert. And we'll go through that here in a little bit. From the load test we've done, we see that it somewhat accurately predicts what this system does. And then after that, we get a flexural loading, and we check that with the CSR equation, whether that's your allowable axial over your available, or available over allowable with the bending and the axial check, whether that's out of the steel manual or any other reference. But here's the round shaft with the core casing insert. So the pipe is that red 5.5, whatever diameter pipe it is, filled with grout. And then the exterior is generally, we use the diameter of the displacement head. So to us, that's what that looks like. You do have grout outside of it, so it helps in L-Pile with the deflection with the springs, the soils model of springs. So we make our casing diameter what our grout column is, and then we just don't give it a thickness. And then so it just models it as a grout column, and then our core diameter and our core wall thickness there. And plain concrete, no rebar. And then our steel properties are, you know, our core inserts an 80 KSI material, and it's pipe filled with grout. So with that, for those of you that have used this, it puts out a deflection and a bending moment, and you can see the shear load that I put on those. So I have, generally what we do is, in this case, in my theoretical case, this is a free head condition. The building code says the allowable lateral load is half the load that produces 1 inch. So usually we check this thing for 2 times lateral to make sure it doesn't go over 1 inch. This is kind of where we start with our design. And so that'll put out, you know, I have my required axial strength, my required flexural strength for my graph back there, the output on that moment. And then the one that we may use the ASC 360 chapter H interaction equation. You know, we'll start with the plastic section modulus. I tell you know, engineers, just be careful. I came from the power industry where they didn't, and this may have changed since it's been a decade or so, but they stay with the elastic section modulus, the S, not the Z in that industry. So, and some engineers don't want the A9ths reduction on the bending. So it's a good discussion to have up front with the team to make sure we're all on the same page. So that's the basics of the structural design: axial, lateral, pretty straightforward stuff with commercially available software. So the geotechnical design was a little more challenging. Originally, we were using some stuff based on what load tests and things like that. And to me, from a design standpoint, I really wanted to have a good reference I could point to. The DFI, the Deep Foundations Institute, did a pretty cool paper a while back on specifically drill displacement piles. And it was about, they might have had 12 or 15 different ones. And they went through all these load tests and tried to figure out what the best way to predict capacity was. They had a couple of them that met up with our specific one that I went through a load test database, and understanding that some of these things, all these displacement micropiles, are a little bit different in their own way, so it doesn't work for predict everyone just accurately. But the one that I found that kind of does match up pretty well with this particular pile is a equation and research by Willie Neesmith. In mostly sandy soils, and it's empirical based on your blow count or your cone there. So you get 100 times your blow count, and then if you have sandy soils with uniform and well graded, you can get an extra 1,000 PSF of skin friction in sandy soils if that's the case. So you have to have a good boring, obviously. You have to have a blow counter or CPT, and you have to understand the gradation of your soils. So a simple, there's a nice picture of a Stelcore that was exhumed, but a very simple theoretical. We generally don't get sands or soil borings with 18 blow count sand all the way down, but just to kind of go through the exercise here, if I have a corrected blow count of 18 and I'm going in with my 16-inch diameter 50361 wall, and I have little to no fines, well-graded sand. I run my calculation there, 100 times 18 plus that 1,000. That's roughly 20 psi. So my grout column and my bond length there, pretty straightforward calculation. 350 kips ultimate. Besides understanding what structural equations we're using, whether it's out of the steel manual, this is always the conversation that should be had up front too. What kind of factor safety are we looking for? We generally load test our piles on 95% of our projects. So most engineers will say, well, if you have a good load test, a factor safety of 2 is okay. But it's factor safety of 3, we design using that too. So it's just a conversation we have up front. So for cohesive soils, it was a little more challenging. I had to get out my textbook by Donald Caduto and was reading through there about that. And he had this in here about these displacement piles that should be at least equal to or somewhat greater than the driven pile. So as many of us do, whenever you need a good reference, the FHWA has done a great job of putting together these design manuals and references with a lot of good information in there. So I went into that and I started looking around at, again, our load test database and the different ways that the methodologies they had to predict capacity. And you can see there, it depends on a few things, but this married up pretty well with what we do. And obviously it depends on your strength of your clay and your dimensions and your depth and stuff like that. This says up to 3.5 KSF. And I should have mentioned this about the sands too. FN max, I think, is like 30. It won't let you go more than like 30 PSI or 35 PSI with your bond strengths. This limits you up to 3.5 KSF in clay, which makes sense to me too. Is another reason why I like these methodologies, because if I'm using a bond strength of 50 PSI, I'm probably going into some very dense sand or some very stiff clay. And if you remember, we have torque limits on our piles. So these limits on these bond values they make sense to me for what we're doing. So if I had the same kind of little setup here where I got my 16-inch diameter and I'm in 2 KSF clay, good clay, and my diameter is 16 inches and my depth is 30 feet. So you go over to that graph over there with my shear strength of 2 KSF, and I'm doing the, not the smooth steel piles, the corrugated, rougher kind of values there at 30. So I'm pulling off a bond value from that graph, roughly 10.5 PSI, 11 PSI, which makes sense. We do get very good numbers out of sand. We get good values out of clay too, but generally don't pick as much friction up in clay. So doing the same math there, again, where I had 350 in my imaginary case in sand, and this one I got 190 kips. Still a pretty good geotechnical load. The quick and dirty method is we got this manual, this table out of the FHWA. So FHWA type A is a gravity grouted pile. Type E, I believe, is the hollow bar type pile. We kind of live more in that, our load tests show that we live more in that type E with our performance of our piles. Here again, though, not going up into 40 or 50 PSI, lower middle range when we're in this type of soil here. So if you're not sure and you just want to know, I wonder how deep this thing would go. Would it be 70 feet or 30 feet? You know, you could grab a number off of here somewhere in the lower middle range, depending on your soil type, and that would give you a good idea. It doesn't replace having one of us engineers look at it and try to put together a complete design for you or a load test, but it's a good way to estimate the depth. So that's design. I have a couple case studies where you might, if you're in these situations, this might be a good option for you. This one was up in Minnesota, so a paper mill, an upgrade. We had some CPTs done, 15 foot of unsuitable soil, some silty sand, some clay, shallow groundwater. So we had 160 kips in compression. We had some tension-only piles that were 60 kips. So decent sized loads, challenging soil conditions, and we also had a site access challenge. You can see here we had to fly that cat in there to get it inside this building. So the access to get higher loads like that requires larger equipment, but this is the solution that we came up with. The owner of this mill did not want to shut his mill down, and he didn't want disturbance for his equipment. He didn't want people banging in piles. Spoils were going to be difficult to haul off if you brought something out of the ground. As you can imagine, trying to get something in there to get around all that equipment down there would be a challenge to haul the spoils off. So with all these combinations of things here, this is a great opportunity for this drill displacement pile system. And there's our CPTs for the geotechs in the group there. You can see we're getting a little bit better clay down here at the bottom, some denser sand. We were 5 feet below grade, so our tip was down there at 105 feet. So a rather deep steel core pile. I think we used a pretty conservative value for bond. The load tests don't show that we used much end bearing, so we neglected that anyway, but we are getting to some dense stuff down there at the bottom. So for this, like I said, we were 100 foot long with our compression piles with the 12-inch diameter. 60 kips, we had 30 foot long for the tension piles. We added this barrel form on here and soft squeezing clays. We generally add that on just to keep the hole open long enough. There was a project in Texas where it was a windmill farm, and just we're not getting the grout take that we wanted. And one of the founders of the company who has a patent on this came up with this idea. I think he was watching somebody do pottery or something else, just to keep the thing open just long enough. So he put this on here, and we got the grout take that we wanted that was close to our theoretical. So that's an adjustment that was made to this particular system in soft squeezing clays. And we include that in soft clays now when we have that. So we did some load tests. So 320 was our ultimate. It did move. I mean, we'll just call that 0.3 of an inch at your ultimate load. We got excited. The people in the field, the team from Ideal and the inspectors got excited and said, well, let's take this baby to failure and see what happens. So we got up to 400 kips there, and we're at 0.4 of an inch. And the contractor, their superintendent, he was probably the smartest guy in the field that was out there that day, said, you guys can keep pushing on this thing, but that rack, that load test frame is starting to move. And he goes, I'm going in the other room because I don't want to get hit by something. So I think it's cool when you can actually find a failure load, because that tells you what your true factor of safety is. We tried to, but I think they decided to use a little more common sense, and they unloaded it from there. So if I would have went through, just using something out of my textbook, I would have calculated the settlement to be about 0.4 of an inch at service. So this thing, and the third-party engineer that evaluated this load test just said that the geotechnical capacity was so high that it didn't really even keep up with its elastic deformation of the pile shaft. So very good load test. The tension test also didn't really go very far at service, 3/16 of an inch or so at 2 times, and a good rebound there. So very good load test and successful project for us. This project was in New York, Draper Hall. This was one where I believe, there was next to an existing building, and there was a school there, and it was spec'd micro piles and then driven piles, and they didn't want to drive the piles right next to the existing school. And the driven piles were actually spec'd to go like 130 feet. So we looked at it, and there was 30 foot of unbonded, and I do think they did tell me that they were able to get a bond breaker down that deep. So we had a 40 foot bonded length, 70 foot total, compared to the driven piles that were going to go roughly 130 feet. And we went that way because we had some pretty good sand to bond in down there with an average blow count of 25. We used a bond value of 20 PSI on that sand. And then we did a load test, New York City's hold test, where you hold it for 24 hours. So 3/10 of an inch at service, 8/10 after the 24-hour hold, which met their requirements. So it was after this one where I started going back and back calculating what I thought using all pile. We'll look at that later. What I thought how I could modify all pile to predict how this particular pile performs. So we'll look at that in a little bit here, but another very good load test for us there. This is the third one and I believe final one. This one was unique in that we had a 20 kip lateral load per pile. We worked with the structural engineer record to get it high up enough in pile cap and get some reinforcement under it to model it as a semi-fixed head condition, 50% fixity. You can see our loads there. You can see that 1600 diameter with a 7-inch, almost half-inch thick wall. That's because we had that lateral load and the stresses induced from that. We had these little higher steel core, beefier steel core shafts. So we had some unbonded there too, underneath some dense sand and shallow water table. This was one project where we knew we're not going to be able to get as deep as we wanted with pure friction. And I can't remember the number. It was either 8 to 10 kips is what we needed for end bearing. We had an 18-inch diameter plate down there. We thought we're going to hit that. We felt comfortable with it that we may get some end bearing. And I do think if you look at the load test, the load deformation curve here, right at the end there, we are starting to take off where end bearing may be getting activated. But still, we've only moved, a 1/3 of an inch on that. Our criteria was a 1/2 of an inch at 330 kips. So still a very good load test for us. Like I said, there's very dense sand at the tip on that one. Part of our research and development is going through our load test database, not only having calculations that we can refer to, but going through our load test database and trying to recreate some of these load tests in silts and clays and sands and stuff like that. All Pile's a pretty user-friendly software, also by NSoft. It's cool in that you can define a zero friction, no bond zone, which we have a lot. You can have zero end bearing tip resistance. We've modified some of the factors in here about rough and concrete sections and stuff to recreate what we've actually measured in the field. So like I said, at Draper Hall, this thing predicted 0.24 and it was actually 0.29. So maybe one of the smartest things I heard in grad school was an instructor said, if you can predict the deflection of a deep foundation in soils, in difficult soils within a few percentage points, just throw your hands up in the air and tell everybody what a good job you did. So that's what we're trying to do here. So in conclusion, we'll leave some time for questions or discussion. In our sands, obviously we have some bond, we need to calculate some bond values. We must understand our soils. We have to have a good soils report. One thing we do understand, because when we've done these types of piles and groups, we do get some ground improvement. That's something that we're currently studying with some geotech firms and university in California too, to understand what kind of ground improvement we get and how far, many diameters away from it do we see that improvement and to what extent. Clays and silts, we use similar methods for driven piles. And because it's not a smooth column, we generally get very good performance out of it. And then, like I said, installation, our contractors, our partners that we install with, they'll be trained. They do some online training and we do field training. And then somebody from Ideal and Intech will be out there the first few days. And a quickly review again, the cases where you may see a project, maybe you have higher loadings, you have lateral loads or difficult soil conditions where you might want to give Intech a call. Overhead access, side access spoils, the vibration in your structures is a big thing, especially in your older cities where those brick and masonry buildings have been there for a while. Relatively quick installation too. Like I said, 400 or 500 feet a day is a decent ballpark number to use. And then, we do the designs. We looked at some of the load capacities, and like I said, predictable performance in similar soil conditions because it's a mechanically displaced pile. And Sam, I'll let you jump in with anything or if there's any questions.
Yeah, I mean, first I guess we'll get through these few slides. So as always, we'll send out a link to all the participants to a quiz. We'll probably send that out later today. And fill that quiz link out, and that's how you get your PDH credits. And then skip to the next slide here. I think that's a repeat, actually. Skip to the next slide, and then we can open the floor to any questions. Not seeing the chat box light up or anything, so I assume we don't have any questions. Yeah, well, thanks, Nathan, for that very thorough overview of cell core piles, and I thought it was pretty informative. And I think there's huge upside to using these piles as a replacement on some AutoCast projects. So, if you run across an AutoCast project, higher capacity, maybe a little bit too high for a helical, may be a good fit for something like this. So, as feel free to reach out to us. Go ahead, Nathan.
Yeah, and that's the thing is, not having a, in contracting, the big thing too with the AutoCast guys is we understand, and they flat out told me like, hey man, if I can set up my AutoCast rig in the middle of the field, I'm going to do that all day long. And I said, I completely understand. But when you get in situations like we talked about, this is definitely a good option. And the one that kind of, I guess I should have thought about it, there's a cost point there to bring out your AutoCast rig. If you can do half the job with AutoCast and the other half is limited access or something like that, there's a cost point to where they just moving that rig costs so much. It's, even though maybe this pile is a bit more expensive than a traditional AutoCast pile, that you can do the whole job for a little more cost effective than by bringing out two different rigs or two different machines. So.
That's a great point. Yeah, I mean, there's many circumstances that might lead to this being the best sort of mousetrap for the project. So, if you think it might be a good fit, always reach out and we'll explore that option for you guys. So yeah, if there's no questions, again, thanks everybody for joining us today. Look for that quiz link to get your PDH credits, and we look forward to having you again for the next webinar. So yeah, we'll wrap it up here. Thanks everybody.
Thanks everybody for your time. I appreciate it.